Okay, we have the last set of notes today before the test, and what we have to go over today are 4 short gas concepts. So we have 4 separate things to talk about, but each of them is pretty short and little, so we'll do them all in one day. A couple of these you're going to use when we do our lab tomorrow and when you do your lab calculations on Thursday. So we're going over them today, so you have everything you need. First, we've already tried this problem. This problem was your bell ringer this morning. Using the ideal gas law, find the volume of 1 mole of gas at STP. So, when you did this, you were looking for volume. You knew that N was 1 mole. Temperature was 273. Pressure, you could have picked any of your standard pressures or either of them that go into the ideal gas law that we used yesterday. I used the atmospheres one because it makes the math easier, but that's the only reason. And then you pick the R value that matches accordingly. What did we get for the answer for this? 22.4. 22.4 liters. Does it say anywhere in this question what gas this is? No. Would it change any of the numbers if I said it was hydrogen or oxygen or carbon dioxide? No, not really. All of these numbers would stay the same. None of these numbers up here have anything to do with what substance it is. That's kind of interesting. You could solve the same problem for any gas that exists, just like you did for your bell ringer, and you would still get 22.4. It turns out that this is kind of a special number. It has its own name, and we can use it as a conversion factor, because 1 mole of any gas at STP would have a volume of 22.4 liters. It didn't say anywhere in the question what gas that was, and it really wouldn't matter. Any gas at STP, where you have 1 mole, will have a volume of 22.4 liters. This is also known as the molar volume. Kind of makes sense. The volume of 1 mole. When we do our lab tomorrow, we will be attempting to calculate or see how close we can get to this number. So by doing a lab procedure, we're going to see how close we can actually get to 22.4 liters. This leads us to one of our short ideas, and that's called Avogadros Hypothesis. We've heard of this guy twice already. What's he known for?
That one big number.
The big number. What is the big number?
Like 22 or 100.
6.02 times 10 to the 23rd, but what does that tell you?
The number of moles are in one atom.
Number of things that are in a mole. Avogadro is usually known for dealing with the number of particles or dealing with moles. And again here, he's kind of known for that same thing. Avogadros hypothesis says that if you have 2 gases of equal volumes at the same temperature and pressure, then they have the same number of particles. This should make sense if you just take a little bit of time to think about the 4 gas law variables that we have. This statement says that you have 2 gases that have equal volumes, so volume is constant. They also have the same temperature, so temperature is constant, and pressure is constant. If 3 out of your 4 things are the same, is there any room for the 4th to be different? No, think about algebra. If 3 things on the side of the equations are the same, the 4th one has to be, because we set up all of these variables as equations. We said this side has to equal that side. So if 3 of them are the same, the 4th one has to be the same. And if the number of moles is the same, so is the number of particles. Just a quick little visual here. If you had two balloons and one of them had a liter of helium and one of them had a liter of neon, you would have the exact same number of atoms in each balloon, assuming you're holding the balloons side by side. Same temperature, same pressure. This hypothesis is the reason that that 22.4 liters always comes out as 22.4 liters. Regardless of what gas you were to use for that problem, this hypothesis is the reason that the substance doesn't matter. It doesn't matter if you use oxygen or hydrogen or carbon dioxide. The number of particles in each container would be the same, as long as you have the same volumes. So how do we use this idea? What is this for? We can use this 22.4 liters at STP to make some of our gas calculations a lot easier. The key here is that you have to recognize that this 22.4 liters, the math that I'm going to show you, is only good when you're at STP. If you're not at STP, then you have to use one of the other equations we've already learned. So, let's see an example. What can we do with this? What is the volume of 2.5 moles of oxygen at STP? We know that at STP for gases, 1 mole is equal to 22.4 liters. That's a conversion factor. Conversion factors mean factor label. How do we start factor label problems? With the number that is given in the question. So start with 2.5 moles. We need to cancel the moles, so those go on the bottom. We're looking for liters, so we put our 22.4 liters on the top. And then we just have to multiply. Check your sig figs, and you get 56 liters. You could solve this exact same problem with the ideal gas law that we learned yesterday. There's nothing wrong with that, but I think most of you would agree that this math right here is a little bit faster than the ideal gas law. So if you can take a shortcut, go ahead. If it works, you might as well use it. Let's try one more of these. How many moles of gas is 70 liters of nitrogen at STP? What should you start with? 70 liters. Liters need to be canceled, so where does the 22.4 go? On the bottom. What goes on the top? 1 mole. Check your sig figs. This time we're dividing. You should get 3.13 moles. If you have questions about how to use that, just remember, you have to be at STP. If you're not at STP, you have to use a different equation. Okay, gas concept number 2. Dalton's Law of partial pressures. This has to do with having a mixture of gases in one container. Dalton's Law says that the overall pressure of a mixture of gases is equal to the sum of the partial pressures of the gases. By itself, this is not a complex idea. If I had a balloon, and in the balloon I had oxygen and nitrogen and hydrogen, and I asked you to find the total pressure inside the balloon, your first thought would probably be, okay, total means add. Just like math. Add up the pressure from the oxygen, add up the pressure from the nitrogen, add up the pressure from the hydrogen and get the total. By itself, this is not a complex idea. The total pressure in a container equals all of the separate pressures added up. Partial pressure is just a fancy way of saying the contribution of each gas in the mixture. How much pressure comes from the oxygen? How much pressure comes from the hydrogen? There are 2 things about putting this idea into practice that sometimes confuse students. One of them is what the equation looks like. The total pressure in a container is equal to all of the partial pressures added up. But this equation changes depending on how many gases are in your container. If there's only 2, then you have 2 things to add together. If there's 3, then you have to add 3 things. If there's 4, then you have to add 4 things. So the first kind of stumbling block with this is that the equation may look different for every single problem. You have to decide how many gases are in that container, how many things do I have to add up. Okay, the second thing that sometimes trips up students when they do these problems is really simple. If you're going to add up all these pressures, the units have to match. Story problems don't always give you matching units. So you may have to convert from one pressure unit to another before you can set up your equation. And we've practiced that a couple of times with our bell ringers. So hopefully that won't be too big of an issue this year. So let's do an example. Air contains, among other things, oxygen, nitrogen, carbon dioxide, and a whole bunch of other gases that we'll just lump into one category. We'll call that the other category. What is the partial pressure of oxygen if the pressure of the nitrogen is 79.1 kPa, pressure of the carbon dioxide is 0.04 kPa, and all the others together are 0.94 kPa? Remember that atmospheric pressure, or standard pressure, is 101.3 kPa, and that is written, that last one is written in your chart, the very first chart that we filled out. So of the numbers that are given here in the question, which one is the total? The 101.3. And how many pieces do we have to add together to equal that?
The 4.
4. Oxygen, nitrogen, carbon dioxide, and others, whatever those others are. Did all of our units match?
Yeah.
Yeah. So once you've got your equation, you've checked to see that all your units match. This is a pretty easy equation to solve. All you have to do is add and subtract. 101.3 was our total. We're looking for the pressure of the oxygen, and we need to add together our other 3 components. You could double check. If you add and subtract correctly, you should get 21.2 kPa. Side note for your lab tomorrow. We will be collecting a gas, hydrogen is what we're going to collect, over water. That's the easiest way to collect a gas in a lab activity. If you think about trying to collect a gas and measure how much there is, you have to have a container of some kind, and you have to have a way to seal that container. Maybe we could come up with some sort of balloon apparatus, but collecting it over water is a lot easier. Essentially, you have your container upside down in another container of water, and you collect the gas into one container, and the water at the bottom kind of seals out everything else. This will make a little more sense when we do our lab tomorrow. But if the gas is collected over water, then there are going to be 2 components to your mixture. And the total pressure inside your container would be equal to the pressure of the gas you're trying to collect, plus a little bit of pressure from water vapor. Anytime you have water vapor. So there's a little pressure from water vapor there as well. You could just put this off to the side somewhere. You'll need this for your lab calculations. Idea number 3, Graham's law of effusion. Effusion sounds a lot like the biology term diffusion, and they are kind of related. So first, before we actually go over the law, let's go over a little bit of vocabulary. Diffusion occurs where you have molecules moving from areas of high concentration to areas of low concentration. Diffusion is the same idea that allows these little oil fragrance things to work. You put the oil in the bottom, the scent travels up through the sticks that you put in it, and then that scent diffuses throughout the whole room. It makes it smell nice. Effusion is just a little bit different. Effusion involves molecules of a gas escaping through a tiny hole. So if you had a membrane or a balloon, something with a very tiny hole in it, and the gas could escape through that hole, that's what is called effusion. They're similar ideas, but they're not quite the same. Graham's law of effusion actually says that lighter gases effuse and diffuse, could apply the same idea, faster than heavier gases. Lighter gases travel faster than heavier gases. When you think about the velocities of the molecules, it would probably make sense that lighter molecules would be able to move from one place to another faster. Let's do a quick example. Between oxygen gas and chlorine gas, which one would travel faster? Oxygen, because it weighs less. It's a pretty simple idea. Lighter gases travel faster than heavier gases. One more idea to go over, and that's how a barometer works. We're kind of crossing over into earth science a little bit with this. We talked about barometers last year in earth science when we talked about weather, but we didn't really describe how they work. Now that you have a little better understanding of gases and their behavior, we can look at how a traditional barometer actually works. Hopefully, you remember from earth science that a barometer is used to measure atmospheric pressure. Sometimes you hear them talk about it on the news when they're giving the weather forecast. The barometer is falling, the barometer is rising, and from that they can predict what kind of weather we're going to have. A traditional barometer involves a tube of mercury turned upside down into a dish of mercury. You don't see traditional barometers very much anymore because mercury vapors are toxic, and they try to keep mercury out of especially schools and homes. But this is what a traditional barometer would have been. Think about like a giant upside down test tube full of mercury, and then a dish of mercury at the bottom. And the way that you would set this up is to take the giant test tube, fill it all the way to the top with mercury, totally, completely full. And you'd flip it upside down and turn it upside down into the dish at the bottom. When you did that, when you turned it upside down, some of that mercury would fall out into the dish. What keeps the mercury still in the column is the atmospheric pressure on the outside. If you think about the magic beakers that we did, the atmospheric pressure on the water in the outside beaker pushed the water up into the little beaker. It's kind of that same idea. The higher the atmospheric pressure on the outside, the more mercury is going to be standing in the column. When you have a little bit of space at the top, some of the mercury has fallen out, there is nothing in that space any longer. That would be a vacuum. Because if you filled the tube all the way to the top to begin with, there was nothing else in there except mercury. Some of the mercury falls out. Whatever's at the top is now empty space. And this is where we get our standard pressure of 760 millimeters of mercury. Because the pressure that we live under all the time, approximately 1 atmosphere's worth of pressure, will support a column of mercury 760 millimeters high. So the weight of the mercury in the tube is supported by the atmospheric pressure on the outside. The higher the atmospheric pressure on the outside, the higher the mercury in the tube.